Hey, everybody. Excuse me. This is our lesson on atomic structure. By the end of this lesson, you should be able to interpret the data presented in the Bohr model diagrams and dot diagrams for atoms and ions of elements 1 through 18. We're actually going to look at this standard over 3 lessons in this unit. So today we're just looking at basic atomic structure. So first off, let's start with what an atom is. So an atom is defined as the smallest unit of an element. So this is the smallest unit that will retain its identity within some sort of chemical reaction. And an element is any of more than over 100 fundamental substances that consist of atoms of only one kind. So these are the substances you see on the periodic table. So like gold, copper, oxygen, those are elements, and each of those elements are made up of atoms specific to that element. A molecule is a collection of atoms that are chemically bound together, and we also refer to what are called formula units, depending on which type of bonding you have. So molecules can be made up of only one element, so like hydrogen gas or oxygen gas are 2 hydrogens or 2 oxygens chemically bound together, written as right here, give me a pen, H2 and O2. Both of those together mean like 2 hydrogens bound together, 2 oxygens bound together. Or they can be made up of different atoms like water, H2O, CO2, things like that. So this is just one of the models of the atom that we've had over history. So now let's talk about one subatomic particle, and this is protons. And each element on the periodic table has a different number of protons within the nucleus, which is what makes them different. So I like to refer to the protons as the fingerprint of the atom. So you change the number of protons, you're changing what atom you're looking at. Protons themselves have a positive charge. The prefix pro means positive. If you change the number of protons, you are changing the element that you're looking at, which is why they don't normally change, except in the case of nuclear physics. So when we get into Unit 6 and we talk about like nuclear decay, that's where you would see the number of protons changing. Our next one is electrons, and electrons are equal to the number of protons in a neutral element. Okay, so in a neutral element, you need to have positives that cancel out with the negatives. So here, if we've got 11 protons in a neutral element, we should have 11 electrons as well, because electrons are negative. If you change the number of electrons on an atom, you will then become an ion, or it will become an ion. It'll either be a positively charged ion or a negatively charged ion. This is what we study in chemistry, is the change of electrons. Our next one is neutrons, and neutrons really don't have to equal out to anything in particular. Like they don't have to be equal to the number of protons or electrons. Almost all elements have neutrons. Hydrogen is one that does not have a neutron. And neutrons have no charge. So neutral, neutron, no charge. And these are also in the nucleus of the atom with the protons. So that should tell you that the nucleus has a positive charge because they've got positive protons and neutral neutrons. So positives and neutrals give you a positive charge. If you change the number of neutrons, you are actually forming what are called isotopes, which are atoms of the same element that only differ by number of neutrons. So here, we aren't changing the chemical properties. We aren't changing anything about them except the mass of your elements. And if you look at this little figure over to the right here, you'll see hydrogen. Basic hydrogen has no neutrons in the center. Deuterium, which is an isotope of hydrogen because it still only has one proton, which makes it hydrogen, but now has one neutron in the nucleus. And then you have tritium, which is another isotope of hydrogen, which has the one proton that makes it hydrogen and the two neutrons. So all you're changing there is the mass of the nucleus. Again, isotopes are defined as atoms of the same element with different numbers of neutrons. And you can use these to calculate what's called the average atomic mass. And this value is the decimal value on your periodic table. So like for hydrogen, it's 1.008. An example here is carbon. So carbon actually has 3 different isotopes, but we're going to just talk about 2 here. So we've got carbon-12 and carbon-14. Both of them are carbon, which means they both have only 6 protons in the nucleus. But where they differ is the number of neutrons. So carbon-12, this number 12 out here is the isotope notation. So you can write this as carbon-12 or C-12. That 12 is your, what we'll talk about in a minute, your mass number, which is your protons and your neutrons added together. So when you've got this number, you subtract your protons to figure out your neutrons. So 12 minus 6 means I have 6 neutrons. And in carbon-14, 14 minus 6 means I have 8 neutrons. So now let's talk about calculations for atoms and numbers that you need to know for these. So the first one is the atomic number. And the atomic number is the number of protons. It's just straight equal to the number of protons, which you can find on the periodic table. It should be the top number in the block of each element. This is also going to be equal to your number of electrons in a neutral atom. You're about to hear my son start crying, sorry. Maybe he'll be okay. The next calculation you need to know is your mass number. So your mass number is the number of protons plus the number of neutrons. This value is a whole number. So this is different from the average atomic mass, which is the one on the periodic table. So this mass number is usually supplied for you. If you need to know number of neutrons, then you do mass number minus atomic number. You've got that electrons are equal to the number of protons in a neutral atom. They will be different, though. They will not be equal on ions. Protons and neutrons have a mass of 1 AMU, which is an atomic mass unit. So they just are equal to 1. Each of them are equal to 1. An electron is so tiny that they don't actually contribute to the mass, so we don't calculate them into the mass. One thing I do want you to know here, and it is on your notes, but it's not in this PowerPoint, is APEMAN. So APEMAN. APE means atomic number is equal to number of protons, which is equal to number of electrons. So here, I'll even underline it. APE. Okay. And then MAN, M-A-N, is going to be, this one's out of order, but it's going to be mass number minus atomic number equals neutrons. So M-A-N. APEMAN. It's just a way to help you remember how to calculate these values. So now we've got an example problem. So we want to know the atomic number of sulfur. Okay. So first we have to remember that the atomic number is equal to the number of protons. When we remember that, we can then find sulfur, which the name and the symbol is on the periodic table. So sulfur, which is S, find it on the periodic table. Locate that number at the top of the block, which is 16, and that is your number of protons. Okay. So now I want you, let me shrink my picture down here. I want you to try to find the mass number and number of neutrons of sulfur. And for this one, I'm going to make it, oops, let me go back. Hold on. I'm going to make an adjustment to this. We're going to make this sulfur 32, because I think that's what it is in your notes. Okay, so sulfur 32. Pause this and go ahead and try that for me.